Hello there, and welcome to Cosmic Drift, the channel where we explore the wonders of space in the most peaceful way possible. Tonight, we're taking a journey to our closest stellar companion, the magnificent sun that rises each morning and sets each evening in endless rhythm. We'll discover gentle facts about this glowing orb that has watched over Earth for billions of years, facts that will carry you softly towards sleep like warm sunlight filtering through curtains on a lazy afternoon. The sun isn't just a ball of fire in the sky, it's a cosmic furnace, a stellar engine, and the gentle heartbeat that keeps our entire solar system alive. Tonight we'll uncover secrets about solar winds that whisper across space, the quiet dance of magnetic fields, and the peaceful processes that have been humming along for longer than life has existed on Earth. Some of what we'll explore will feel familiar, like the comforting warmth you feel on your skin during a summer day. Others will be wonderfully surprising, like discovering that our sun sings songs we cannot hear, or that it breathes in cycles longer than human civilizations. But each fact will be like a soft melody designed to ease your mind and remind you of the vast, serene universe that surrounds us all. As we drift through these solar discoveries, you might find your thoughts becoming as light as particles of sunlight, your breathing as steady as the sun's ancient rhythms, and your body settling into the kind of deep relaxation that comes from knowing you're part of something infinitely larger and more peaceful than the worries of any single day. If you enjoy these cosmic journeys into sleep, feel free to subscribe and let me know in the comments which corner of the universe you'd like to explore next. But for now, let your mind float like a dust mote in a sunbeam and allow these gentle solar truths to wash over you like golden light. Let's begin our peaceful voyage to the heart of our solar system. The sun is actually white, not yellow. When you picture the sun in your mind, you probably see a warm yellow or orange orb. But beyond our atmosphere, the sun appears as a brilliant white star. The yellow and orange hues we see from Earth come from our planet's atmosphere scattering the sun's light, filtering out some of the blue wavelengths and leaving us with those warmer tones that feel so comforting to observe. It's like looking through a gentle cosmic filter that softens the sun's true brilliance into something our eyes can appreciate. This white light contains every color of the rainbow, all blended together in perfect harmony, much like how a prism can split sunlight into its component colors, revealing the hidden spectrum that was there all along. Our sun completes one full rotation every 25 days at its equator. Unlike Earth, which spins as a solid unit, the sun rotates more like honey being stirred in a jar. Its equatorial regions spin faster than its poles, creating a gentle, flowing motion that takes about 25 days to complete one full turn. At the sun's poles, this rotation slows to about 35 days. Imagine this slow, graceful spinning motion, like a cosmic ballet dancer turning in the depths of space, carrying its family of planets along in their orbital dance. This differential rotation creates beautiful patterns in the sun's magnetic field, like invisible ribbons wrapping around our star in elegant spirals. The sun generates enough energy every second to power human civilization for millions of years. Deep in the sun's core, nuclear fusion occurs at temperatures of about 15 million degrees Celsius. Every second, the sun converts roughly 4 million tons of matter into pure energy through this process. This energy then begins a journey that can take anywhere from 10,000 to 170,000 years to travel from the core to the surface. bouncing around like a gentle pinball through the sun's dense interior. By the time this energy reaches us as sunlight, it has been on an incredibly long and patient journey, arriving as the perfect amount of warmth and light to sustain life on our blue planet. Solar wind flows from the sun like a cosmic river. The sun constantly releases a stream of charged particles called the solar wind, which flows outward through the solar system at speeds of about 1 million miles per hour. Despite this incredible velocity, solar wind is actually incredibly thin, more tenuous than the best vacuum we can create on Earth. If you could somehow stand in this cosmic breeze, you wouldn't feel it at all. Yet this gentle stream of particles creates the beautiful auroras we see at Earth's poles when it interacts with our planet's magnetic field, painting the night sky in curtains of green, blue, and pink light that dance like cosmic silk scarves in a celestial wind. The sun's surface temperature is about 5,500 degrees Celsius, but its corona is over 200 times hotter. This seems to defy logic, like finding that the air above a campfire is somehow much hotter than the flames themselves. The sun's corona, its outer atmosphere, reaches temperatures of over 1 million degrees Celsius, creating one of the most beautiful mysteries in solar physics. Scientists call this the coronal heating problem, and while we don't fully understand why this happens, we can observe its effects during solar eclipses when the corona becomes visible as a shimmering, pearlescent halo around the darkened sun, like gossamer threads of superheated gas dancing in space. Every 11 years, the sun's magnetic field completely flips. Like a cosmic clock, our sun follows an 11-year cycle during which its magnetic north and south poles gradually reverse positions. During this cycle, the number of sunspots on the sun's surface waxes and wanes like a slow tide. At the peak of this cycle, called solar maximum, the sun's face is peppered with dark sunspots and erupts with solar flares and coronal mass ejections. During solar minimum, the sun's surface appears much calmer and cleaner, with few sunspots visible. This gentle breathing of our star has been observed for centuries, a reminder that even our seemingly constant sun has rhythms and cycles as regular as breathing or a heartbeat. Sunspots are actually cooler than the surrounding solar surface. These dark patches that appear on the sun might look like blemishes, but they're actually regions where intense magnetic fields have cooled the surface temperature by about 1,500 degrees Celsius. While this makes them appear dark against the brilliant background, sunspots are still incredibly 4,000 degrees Celsius. If hot, glowing at about, you could somehow remove a sunspot from the sun and place it alone in space. It would shine with a reddish light brighter than a full moon. Some sunspots grow larger than planet Earth, creating vast, cool islands in an ocean of nuclear fire that can persist for days or weeks before gradually fading away. The sun makes sound, but we cannot hear it. Deep within our star, convection currents create pressure waves that propagate through the solar interior, much like sound waves traveling through air. These solar oscillations cause the sun's surface to rise and fall by tiny amounts, just a few meters, in patterns that repeat every 5 minutes. Scientists study these vibrations through a field called helioseismology, using the sun's own music to peer into its hidden interior. If we could somehow hear these solar songs, they would sound like deep, resonant tones far below the range of human hearing, like the lowest notes of a cosmic organ playing an eternal chord in the depths of space. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. When you step outside and feel sunshine on your face, you're experiencing light that left the sun's surface just over 8 minutes ago. This means we always see the sun as it was 8 minutes in the past, never as it is in the present moment. If the sun were to suddenly disappear, we wouldn't know for 8 minutes and 20 seconds, continuing to receive light and heat from a star that no longer existed. This 8-minute journey represents the cosmic speed limit, the fastest that information can travel through space, connecting us to our star across 93 million miles of vacuum with threads of light that bridge the gap between worlds. The sun contains 99.8% of all the mass in our solar system. Despite the presence of 8 planets, countless moons, asteroids, and comets, our sun is so massive that everything else combined makes up less than 0.2% of the solar system's total mass. Jupiter, the largest planet, contains about 70% of all the planetary mass, yet the sun still outweighs it by over 1,000 to 1. This incredible gravitational dominance is what keeps all the planets in their orbits, like a cosmic anchor holding the entire solar system together, in a delicate dance that has continued for over 4.5 billion years. Our sun is classified as a yellow dwarf star, though it won't stay that way forever. In stellar terms, our sun is considered middle-aged, having burned steadily for about 4.5 billion years, with roughly another 5 billion years of stable hydrogen burning ahead of it. During this time, it will gradually grow brighter and larger. Eventually, when the hydrogen in its core is exhausted, our sun will expand into a red giant star, growing so large that it may engulf the inner planets. But this transformation is so far in the future that it's almost impossible to comprehend, occurring over timescales that dwarf all of human history thousands of times over. The sun's gravity is so strong that it could compress you into a point smaller than an atom. If you could somehow survive the intense heat and radiation and fall toward the sun's center, the gravitational forces would become unimaginably powerful. The sun's gravity at its surface is about 28 times stronger than Earth's, meaning a person who weighs 150 pounds on Earth would weigh over 4,000 pounds on the sun's surface. As you fell deeper into the solar interior, the gravitational compression would become so intense that atomic structures would break down completely, demonstrating the incredible forces that govern our star's existence. Solar flares can release as much energy as billions of nuclear bombs. When the sun's twisted magnetic field lines suddenly snap and reconnect, they can release enormous amounts of energy in the form of solar flares. These eruptions accelerate particles to nearly the speed of light and can heat plasma to temperatures of tens of millions of degrees. The largest solar flares, classified as X-class events, release energy equivalent to billions of hydrogen bombs exploding simultaneously. Yet even these violent events appear as mere flickering brightnesses when viewed from Earth, reminders of the awesome but distant power of our star. When these energetic particles reach Earth, they can create spectacular auroras and occasionally disrupt satellites and power grids, connecting us directly to our star's magnetic moods. The sun is approximately 4.5 billion years old. To put this vast timescale into perspective, if the sun's entire life were compressed into a single year, human civilization would have existed for less than the last second of December 31st. The dinosaurs lived during the final week of December, while complex life on Earth only appeared in the last couple of months. For most of the sun's existence, Earth was a very different place, with different atmospheres, different continents, and different forms of life. Yet through all these changes, the sun has burned steadily, providing the consistent energy that allowed life to evolve, flourish, and eventually develop the consciousness to look back and contemplate its stellar parent. Every atom in your body, except for hydrogen, was forged in the heart of a star. The carbon in your muscles, the calcium in your bones, the iron in your blood, all were created through nuclear fusion in the cores of ancient stars that lived and died before our sun was even born. When these massive stars reached the end of their lives, they exploded as supernovas, scattering these heavy elements throughout space where they eventually became incorporated into new star systems like ours. In a very literal sense, you are made of stardust, carrying within your body the legacy of stellar furnaces that burned billions of years ago. The sun continues this ancient tradition, fusing hydrogen into helium and creating the energy that powers all life on Earth. The sun's core is incredibly dense. At the very heart of our star, matter is compressed to about 150 times the density of water. This means that a teaspoon of material from the sun's core would weigh about as much as a small car on Earth. Under these extreme conditions, hydrogen nuclei are squeezed together with such force that they overcome their natural electrical repulsion and fuse together, releasing the energy that eventually becomes the sunlight warming your face. This fusion process is so efficient that the sun loses only about 4 million tons of mass every second through conversion to energy. Barely a whisper compared to its total mass of 2 billion tons. The sun moves through space at incredible speeds, carrying our entire solar system along for the ride. While we feel perfectly still on Earth, we're actually racing through the cosmos at about 515,000 miles per hour as our sun orbits the center of the Milky Way galaxy. This orbital journey is so vast that it takes our solar system approximately 225 to 250 million years to complete just one trip around the galactic center. The last time we were in this same position in space, dinosaurs hadn't even evolved yet, and the most complex life forms on Earth were simple marine creatures. As you lie here listening to these words, you're a passenger on a cosmic voyage that began before life itself. Learn to walk on land, traveling through star-filled neighborhoods that change so slowly that thousands of human generations pass without noticing any difference in our celestial surroundings. The sun breathes in a rhythm lasting approximately 11 minutes. Scientists have discovered that our star expands and contracts very slightly in a regular pattern, growing larger and smaller by just a few kilometers every 11 minutes or so. This gentle pulsing is caused by sound waves bouncing back and forth through the sun's interior, creating a stellar heartbeat that has been steady for billions of years. If you could watch this breathing from space, it would be far too subtle to see with the naked eye, but sensitive instruments can detect these minute changes in the sun's size. This cosmic respiration reminds us that even something as seemingly permanent as our sun is alive with motion, gently inhaling and exhaling like a sleeping giant in the depths of space. Solar energy reaches Earth in waves that span the entire electromagnetic spectrum. While we can only see a tiny portion of the sun's light with our eyes, our star actually broadcasts radio waves, infrared heat, visible light, ultraviolet radiation, and even small amounts of X-rays and gamma rays. This complete spectrum of energy travels together through space like an invisible orchestra, with each type of radiation carrying different information about the sun's activities. Radio waves from the sun can be detected by special telescopes here on Earth, allowing astronomers to listen to our star's electromagnetic voice. The infrared radiation warms our planet and drives weather patterns, while the visible light powers photosynthesis in plants and creates the blue sky we see during the day through scattering in our atmosphere. The sun's magnetic field extends far beyond what we can see. Like Earth, our sun has a magnetic field, but it's incredibly complex and dynamic, constantly changing and reorganizing itself. This magnetic field doesn't stop at the sun's visible surface, but extends throughout the entire solar system in a region called the heliosphere. Solar wind carries these magnetic field lines outward, creating a vast bubble of solar influence that reaches past Pluto and protects our solar system from most harmful cosmic radiation coming from interstellar space. When spacecraft like Voyager 1 finally left this magnetic cocoon and entered interstellar space, they detected a noticeable increase in high-energy particles from deep space, showing us that our sun has been quietly shielding us from cosmic dangers for our entire existence. Neutrinos from the sun pass through your body every second without you feeling them. Deep in the sun's core, nuclear fusion creates not only light and heat, but also ghostly particles called neutrinos. These nearly massless particles interact so weakly with matter that they can pass through the entire Earth without being stopped. Every second, trillions of neutrinos from the sun stream through your body, passing between your atoms like whispers through an empty cathedral. Special underground detectors filled with thousands of tons of water can occasionally catch one of these elusive particles, providing us with direct information about the nuclear reactions happening in the sun's heart right now. Unlike sunlight, which takes thousands of years to journey from the core to the surface, neutrinos escape immediately, giving us a real-time window into our star's most intimate processes. The sun's influence on Earth goes far beyond light and heat. Our star's magnetic field interacts with Earth's magnetosphere in complex ways, creating space weather that can affect satellites, radio communications, and even power grids. During periods of high solar activity, charged particles from solar storms can penetrate deeper into Earth's atmosphere, sometimes creating auroras visible at lower latitudes than usual and occasionally disrupting the delicate electronic systems that modern civilization depends upon. Airlines sometimes reroute flights over the polar regions during major solar storms to avoid increased radiation exposure. Yet most of the time, Earth's magnetic field deflects these solar particles harmlessly around our planet, creating a protective magnetic shield that has safeguarded life for billions of years. The sun contains enough hydrogen to continue burning for another 5 billion years. Inside our star's core, approximately 600 million tons of hydrogen are converted into helium every single second through nuclear fusion. While this might sound like the sun is rapidly consuming its fuel, the total amount of hydrogen available is so enormous that this process can continue for billions of years without any noticeable change in the sun's brightness or behavior. This steady, reliable energy production has remained remarkably constant throughout Earth's history, varying by less than 1% over geological timescales. This stellar stability has been crucial for the development and maintenance of life on our planet, providing the consistent energy input that allowed evolution to proceed gradually over vast periods of time. Sunlight has been the driving force behind virtually all life on Earth. Through the process of photosynthesis, plants capture solar energy and convert it into chemical energy, forming the base of almost every food chain on our planet. Even fossil fuels like coal and oil are essentially stored sunlight created from ancient plants and animals that originally derived their energy from our star. The wind is powered by solar heating of the atmosphere, ocean currents are driven by solar warming of seawater, and the water cycle that brings rain to continents exists because solar energy evaporates water from the ocean surface. In this way, the sun is not just a distant light in the sky, but the fundamental energy source that powers the entire biosphere, connecting every living thing on Earth to our star through invisible threads of energy that have been weaving the web of life for billions of years. The sun's surface is constantly changing in ways both subtle and dramatic. What appears to be a smooth, uniform disk when viewed through protective filters is actually a roiling sea of hot plasma in constant motion. Granules of hot gas, each about the size of Texas, rise and fall across the solar surface in a pattern that resembles boiling water when viewed through powerful telescopes. These granules form as hot plasma rises from the sun's interior, cools at the surface, and then sinks back down, creating convection cells that give the sun's photosphere a mottled, ever-changing appearance. Prominences arch high above the surface like bridges of fire following magnetic field lines that loop through the corona. Some of these solar prominences can persist for days or weeks, creating graceful arcs of glowing gas that stretch for distances greater than the diameter of Earth. The sun produces its own weather systems that are both beautiful and powerful. Solar tornadoes made of superheated plasma can tower hundreds of thousands of miles above the sun's surface, spinning at speeds of up to 100,000 miles per hour. These magnificent spirals are guided by magnetic field lines and can persist for hours or even days before dissipating. Coronal holes, regions where the sun's magnetic field lines extend into space rather than looping back to the surface, appear as dark areas in X-ray images of our star. These holes allow solar wind to escape more easily, creating high-speed streams of particles that can affect Earth's magnetosphere when they arrive days later. During solar eclipses, the sun's corona reveals its complex structure, with streamers and rays extending in all directions, like the petals of an enormous flower made of light. Human cultures throughout history have recognized the sun's central importance to life. Ancient civilizations built monuments aligned with solar movements, created calendars based on the sun's yearly journey across the sky, and developed mythologies that honored our star as a divine presence. The Egyptian god Ra, the Greek god Helios, the Aztec god Tonatiuh, and countless other solar deities reflect humanity's deep understanding that the sun is the giver of life and the measure of time itself. Modern science has revealed the physical mechanisms behind the sun's power, but this knowledge only deepens our appreciation for the elegant processes that have sustained life on Earth for so long. Every sunrise and sunset connects us to this ancient relationship between Earth and Sun, a daily reminder of the cosmic forces that shape our existence. Solar eclipses create moments of profound connection between Earth, Moon, and Sun. When the moon passes directly between Earth and the sun, it casts a shadow that can briefly turn day into night for observers along the path of totality. During these rare events, the sun's corona becomes visible as a shimmering halo around the darkened solar disk, revealing structures normally invisible against the bright photosphere. The temperature drops, Animals behave as if night is falling and stars become visible in the darkened sky. These celestial alignments occur because of an extraordinary cosmic coincidence. The moon appears almost exactly the same size as the sun when viewed from Earth, despite the sun being 400 times larger and 400 times farther away. This perfect sizing creates total solar eclipses that can last several minutes, offering windows into the sun's outer atmosphere that have helped scientists understand stellar physics and the nature of our cosmic neighborhood. The sun's energy output has remained remarkably stable throughout human history. While our star does have cycles and variations, its total energy output changes by less than 0.1% over the course of the 11-year solar cycle. This incredible stability is one reason why life has been able to thrive on Earth for billions of years. Even small changes in solar output would have dramatic effects on Earth's climate, so the sun's steady burning has provided the consistent energy foundation that allowed complex life to evolve. Climate scientists study these tiny variations in solar output to better understand natural climate changes, but they've found that the sun's variability is much smaller than the changes caused by human activities in recent decades. Our star continues to be a model of reliability, rising each morning and setting each evening with the same gentle constancy that has marked the passage of days since Earth first formed. The sun creates its own magnetic storms that ripple through space like invisible tsunamis. When magnetic field lines on the solar surface become twisted and tangled, they can suddenly snap and reconnect with explosive force, launching billions of tons of charged particles into space at speeds exceeding 1 million miles per hour. These coronal mass ejections travel outward from the sun like expanding bubbles of magnetized plasma, carrying with them the imprint of our star's magnetic personality. When these solar storms reach Earth 2 to 4 days later, they can compress our planet's magnetosphere and trigger geomagnetic disturbances that paint the polar skies with dancing auroras. The largest recorded geomagnetic storm occurred in 1859 when telegraph wires sparked and caught fire, and auroras were visible as far south as the Caribbean. Today, our technology-dependent civilization monitors space weather as carefully as meteorologists track earthly storms, watching for solar eruptions that could affect satellites, power grids, and communication systems. The sun's gravity creates tides not just in Earth's oceans, but in the solid rock of our planet itself. While the moon's gravitational pull is the primary driver of ocean tides, the sun also tugs at Earth with enough force to raise and lower the solid surface by several inches twice each day. These Earth tides are imperceptible to us, but sensitive instruments can measure how the ground beneath our feet rises and falls in response to our star's gravitational embrace. This gravitational dance extends throughout the solar system, with the sun's immense mass orchestrating the movements of planets, asteroids, and comets in an intricate celestial ballet that has continued for billions of years. Even tiny dust particles in the outer reaches of the solar system feel the sun's gravitational whisper, slowly spiraling inward over millions of years in a process called the Poynting-Robertson effect. Solar radiation pressure is so gentle that it can barely move a feather, yet it powers some of the most elegant spacecraft ever designed. Photons of sunlight carry tiny amounts of momentum, and when they strike an object, they exert a minuscule but measurable force. This radiation pressure is what pushes comet tails away from the sun, creating those magnificent streaming displays that have inspired wonder for millennia. Engineers have harnessed this cosmic wind to propel solar sails, spacecraft with enormous reflective wings that catch sunlight like sailing ships catch ocean breezes. These vessels accelerate slowly but continuously, eventually reaching incredible speeds without carrying any fuel. The Japanese spacecraft Icaros successfully used solar sailing to travel to Venus, proving that sunlight itself can carry us to other worlds. As you rest here in the darkness, photons from the sun are gently pushing against every surface they touch, including your skin, with a force so soft you cannot feel it, but so persistent it could eventually carry a spacecraft to the stars. The sun's interior rotates like a cosmic clock with different layers keeping different time. While the surface completes one rotation every 25 days at the equator, deep inside the sun, different regions spin at their own pace. The radiative zone, where energy slowly diffuses outward through countless interactions with matter, rotates almost as a solid body, taking about 27 days to complete one turn. This differential rotation creates a dynamo effect that generates and maintains the sun's complex magnetic field, like a cosmic generator that has been running continuously for billions of years. The boundary between the radiative zone and the convective zone above it, called the tachocline, is thought to be where the sun's magnetic field is born and organized, a hidden layer where solar magnetism takes shape before erupting onto the surface as sunspots and flares. Every sunrise and sunset you've ever witnessed was created by the same nuclear reactions that have powered our star since before Earth existed. The photons that painted this morning's sky in shades of gold and rose began their journey in the sun's core as gamma rays, the most energetic form of light. Through countless collisions and interactions during their long migration through the solar interior, these gamma rays gradually lost energy, transforming first into X-rays, then ultraviolet light, and finally into the gentle, visible light that illuminates our world. By the time they reach your eyes, these ancient photons have been softened and mellowed by their journey through the sun, arriving as the perfect wavelengths for vision, for photosynthesis, and for warming the earth just enough to keep water liquid on our planet's surface. The sun communicates with Earth through the language of magnetic fields. Solar wind carries the sun's magnetic field throughout the solar system, creating what scientists call the interplanetary magnetic field. When this solar magnetism encounters Earth's own magnetic field, the two interact in complex ways that depend on their relative orientations. When the magnetic fields are aligned in opposite directions, they can reconnect explosively, allowing solar particles to penetrate deeper into Earth's magnetosphere. This magnetic conversation between Sun and Earth creates the conditions for auroras, those ethereal curtains of light that dance across polar skies. Indigenous peoples of the Arctic have observed these lights for thousands of years, developing rich traditions and stories to explain their movements and colors, recognizing them as visible signs of the cosmic relationship between our planet and our star. The sun's energy reaches Earth in precisely measured waves that arrive with clockwork regularity. The solar constant, the amount of solar energy received per square meter at Earth's distance from the sun, is approximately 1361 watts per square meter. This value represents the energy the foundation of all Earthjets, the baseline from which climate scientists calculate how much energy our planet receives and how it's distributed around the globe. Seasonal variations in this energy input, caused by Earth's elliptical orbit and tilted axis, drive the grand patterns of weather and climate that shape ecosystems and influence the rhythms of life. Even tiny variations in the solar constant, measured by satellites to incredible precision, help scientists understand both natural climate variations and the human influences that are now changing Earth's energy balance. The sun's magnetic field extends its influence to the very edges of the solar system through a vast magnetic bubble called the heliosphere. This invisible boundary, shaped like a teardrop pointing away from the galaxy's center, marks the limit of our star's dominion and separates the solar wind from the interstellar medium beyond. The heliopause, where solar influence finally yields to interstellar space, lies roughly 120 astronomical units from the Sun, nearly 4 times farther than Neptune's orbit. When Voyager 1 crossed this boundary in 2012, it detected a dramatic change in the cosmic ray environment, proving that our sun creates a protective cocoon around its planetary family. This stellar embrace has shielded Earth and the other planets from much of the high-energy radiation that permeates the galaxy, creating a safer haven for the development of life. Solar scientists have discovered that our sun oscillates in millions of different modes, each with its own frequency and pattern. These stellar vibrations, studied through the field of helioseismology, allow astronomers to peer inside the sun much as geologists use earthquake waves to study Earth's interior. Some of these solar notes have periods of just 5 minutes, while others take hours to complete one cycle. The sun rings like an enormous bell struck by the constant churning of convection in its outer layers, creating a symphony of sound waves that bounce back and forth through the solar interior. By analyzing these vibrations, scientists have mapped the sun's internal structure with remarkable precision, revealing the size of its core, the depth of its convection zone, and the speed at which different layers rotate. The sun's coronal heating mystery represents one of the most beautiful puzzles in astrophysics. Logic suggests that as you move away from any heat source, the temperature should decrease, yet the sun's corona burns at temperatures over 200 times hotter than the photosphere below it. This cosmic paradox has inspired decades of research and multiple competing theories. Magnetic reconnection events might heat the corona through countless tiny explosions, or perhaps waves propagating through the solar atmosphere carry energy upward like invisible messengers of heat. Recent observations by the Parker Solar Probe, humanity's closest approach to our star, are finally providing clues to solve this mystery. As this brave spacecraft skims through the outer corona, it's discovering that the solar atmosphere is even more dynamic and complex than previously imagined, with magnetic switchbacks and plasma flows that defy our expectations. The sun's relationship with Earth extends far beyond the simple delivery of light and heat. Our star's magnetic field interacts with charged particles in Earth's upper atmosphere to create a complex electrical circuit that connects the ground to the ionosphere. This global electrical circuit influences everything from lightning patterns to the behavior of radio waves. The ionosphere itself, a layer of charged particles created by solar radiation, acts like a vast mirror that can bounce radio signals around the world, enabling long-distance communication. Solar activity affects the density and behavior of this ionized layer, sometimes enhancing radio propagation and sometimes disrupting it entirely. Ham radio operators around the world monitor solar conditions as carefully as sailors watch The weather, knowing that a solar flare can either open up new communication paths or close them down entirely. Ancient sunlight preserved in Earth's rocks tells the story of our star's long history. Fossil coral reefs and other marine organisms that built their shells from calcium carbonate captured information about past solar activity in the ratios of different isotopes they incorporated. Tree rings, ice cores, and sedimentary layers all contain subtle chemical signatures that reflect variations in solar output over hundreds and thousands of years. These natural archives reveal that the Sun has experienced periods of reduced activity, such as the Maunder minimum from 1645 to 1715, when very few sunspots were observed, and Earth experienced a period of cooling known as the Little Ice Age. By studying these proxy records, scientists can extend their knowledge of solar behavior far beyond the brief period of direct observation, discovering that our seemingly steady star has its own long-term moods and rhythms. The Sun creates its own space through the continuous expansion of the solar wind. This stellar breeze carves out a cavity in the interstellar medium, creating a region where the Sun's influence dominates over the general galactic environment. The shape and size of this heliospheric bubble depend on both the strength of the solar wind and the properties of the local interstellar medium through which our solar system is currently traveling. As our Sun moves through the galaxy at 19 miles per second, it encounters regions of varying density and magnetic field strength, causing the heliosphere to fluctuate in size and shape over thousands of years. The bow shock that forms where the solar wind meets the interstellar medium is invisible to our eyes, but represents one of the most fundamental boundaries in our cosmic neighborhood, marking where solar space ends and galactic space begins. The Sun's energy sustains not only life on Earth's surface, but also drives the planet's internal dynamics in subtle ways. Solar heating creates temperature differences between day and night sides of Earth that contribute to atmospheric tides, regular oscillations in air pressure that circle the globe twice each day. These atmospheric tides are much smaller than ocean tides, but can be detected by sensitive barometers, revealing how deeply solar energy penetrates into Earth's atmospheric systems. The annual cycle of solar heating also influences the solid Earth through thermal expansion and contraction, causing seasonal variations in the length of each day by tiny fractions of a second, as our planet's rotation rate responds to changing atmospheric circulation patterns driven by solar energy. The Sun's magnetic field lines sometimes form enormous loops that arch high above the solar surface like bridges made of invisible force. These magnetic structures can trap hot plasma, creating prominences that glow against the darkness of space when viewed from the side, or appear as dark filaments when seen against the bright solar disk. Some prominences remain stable for weeks, slowly evolving and changing shape as they follow the Sun's rotation. Others can suddenly erupt, launching material into space at speeds exceeding escape velocity. The largest prominences can extend for distances greater than the diameter of Jupiter, creating majestic arcs of glowing gas that demonstrate the incredible power of magnetic forces to shape and control matter in the solar atmosphere. Human technology has allowed us to see the Sun in wavelengths of light invisible to our eyes, revealing hidden layers of solar activity. X-ray images show the corona's bright, active regions and dark coronal holes, while ultraviolet observations reveal the chromosphere's dynamic structure and the constant rain of material falling back to the solar surface. Radio telescopes detect bursts of radio waves generated by energetic electrons spiraling through magnetic fields, and specialized coronagraphs create artificial eclipses to study the corona's structure and evolution. Each wavelength of light carries different information about solar processes, like viewing the same landscape through different colored filters that reveal details invisible to ordinary sight. This multi-wavelength approach has transformed our understanding of the sun from a simple ball of fire into a complex, dynamic system with layers, cycles, and behaviors as intricate as those of living organisms. The sun's gravitational influence extends far beyond the orbit of Pluto, reaching into the Oort cloud where countless comets orbit in a vast spherical shell surrounding the solar system. These icy remnants from the solar system's formation remain loosely bound to the sun at distances up to 100,000 astronomical units, nearly halfway to the nearest star. Occasionally, gravitational perturbations from passing stars or galactic tides nudge one of these distant comets toward the inner solar system, beginning a million-year journey that will eventually bring it close enough to the sun to develop the glowing tail that makes it visible from Earth. In this way, the sun continues to interact with the most distant members of its family, occasionally calling them home from the cold depths of interstellar space for a brief, brilliant visit to the warm inner regions where planets orbit and life thrives. Solar energy powers the vast circulation systems that distribute heat around our planet, creating the winds and ocean currents that moderate Earth's climate. The trade winds that blow steadily across tropical oceans, the jet streams that guide weather systems around the globe, and the great ocean currents like the Gulf Stream all derive their energy ultimately from solar heating. These circulation patterns help transport heat from the equator toward the poles, preventing the tropics from becoming unbearably hot and keeping the polar regions from freezing solid. Without this solar-powered heat distribution system, Earth would be a planet of extremes, with scorching equatorial regions and permanently frozen polar zones separated by narrow bands of temperate climate. The sun's energy creates not just warmth, but the dynamic atmospheric and oceanic systems that make our planet habitable across a wide range of latitudes. The sun's interior operates on timescales that dwarf human comprehension, with energy taking tens of thousands of years to complete its journey from core to surface. A photon born in the nuclear furnace of the sun's heart begins an epic migration through layers of increasingly less dense material, bouncing from atom to atom in a cosmic pinball game that can last anywhere from 10,000 to 170,000 years. During this incredibly long journey, the original gamma ray gradually loses energy through countless interactions, slowly transforming into the gentle, visible light that eventually emerges from the photosphere. By the time this ancient energy reaches Earth, it has been thoroughly mellowed by its passage through the sun, arriving as the perfect wavelengths for warming our planet and powering photosynthesis in plants. The sun's magnetic field creates invisible highways through space that guide charged particles on journeys spanning millions of miles. These magnetic field lines, stretched and carried by the solar wind, form complex spirals that extend throughout the solar system like the grooves on an enormous phonograph record. Charged particles from solar flares and coronal mass ejections follow these magnetic highways, sometimes taking shortcuts that bring them to Earth in less than a day, while other particles meander along longer magnetic paths that can take weeks to complete their interplanetary voyage. When these solar particles finally encounter Earth's magnetosphere, they create the shimmering curtains of aurora that dance across polar skies, painting the darkness with colors that reflect the inner self. Visible architecture of interplanetary magnetic fields. Solar physicists have discovered that the sun's activity follows patterns within patterns, creating rhythms that span decades and centuries. While the 11-year sunspot cycle is the most well-known solar rhythm, longer cycles lasting 22 years, 88 years, and even longer periods have been detected in historical records and proxy data. These extended cycles may be responsible for subtle climate variations on Earth, influencing everything from the strength of monsoons to the frequency of droughts. The sun's magnetic personality appears to have multiple layers of complexity, like a cosmic symphony with themes and variations that play out over timescales far longer than human lifetimes. Understanding these longer rhythms helps scientists place current solar activity in historical context and may eventually allow for better predictions of space weather and its effects on Earth. The sun creates its own time zones through the differential rotation of its plasma layers. Unlike a solid planet that rotates as a single unit, the sun's gaseous nature allows different latitudes to spin at different rates, creating a phenomenon known as differential rotation. The equatorial regions complete one rotation in about 25 days, while regions at 60 degrees latitude take about 30 days, and the polar regions may take 35 days or more. This differential rotation winds up the sun's magnetic field lines like rubber bands being twisted, storing enormous amounts of magnetic energy that is eventually released through solar flares and coronal mass ejections. The sun's inability to rotate as a solid body is one of the key factors that makes it such a magnetically active and dynamic star. Coronal mass ejections represent some of the most powerful explosions in the solar system, yet they begin as subtle reconfigurations of magnetic field lines in the sun's corona. When magnetic fields become twisted and stressed beyond their breaking point, they can suddenly snap and reconnect with explosive force, launching billions of tons of magnetized plasma into space at speeds exceeding 1,000,000 miles per hour. These eruptions can clear enormous regions of the corona, creating temporary cavities in the sun's outer atmosphere that slowly refill over hours or days. The largest coronal mass ejections can affect the entire solar system, compressing planetary magnetospheres and creating geomagnetic storms that persist for days after the initial eruption. Despite their incredible power, these events often appear deceptively gentle when viewed through special telescopes, like vast bubbles of light slowly expanding away from the sun. The sun's influence on Earth's climate operates through mechanisms both obvious and subtle, from the direct heating that drives weather patterns to the indirect effects of solar variability on atmospheric chemistry. Changes in solar ultraviolet radiation, though representing a small fraction of the sun's total output, can significantly affect the formation and destruction of ozone in Earth's stratosphere. These ozone changes alter the temperature structure of the upper atmosphere, which in turn influences circulation patterns that can affect weather at ground level. Solar energetic particles, accelerated by solar flares and shocks in the solar wind, can also affect atmospheric chemistry by creating additional pathways for ozone destruction. These complex solar-terrestrial connections mean that space weather and earthly weather are more intimately linked than most people realize. The sun's rotation creates a cosmic spiral pattern in the solar wind that extends throughout the solar system. As the sun spins on its axis while simultaneously ejecting solar wind, the result is a pattern known as the Parker spiral, named after the physicist who first described this interplanetary magnetic structure. Fast solar wind from coronal holes and slower wind from other regions create a complex pattern of high and low-speed streams that rotate with the sun like the arms of a slowly turning pinwheel. When Earth encounters the boundaries between these different wind streams, it can trigger minor geomagnetic disturbances and enhance auroral activity. This rotating pattern means that space weather often has a 27-day recurrence tendency, matching the sun's rotation period as seen from Earth. The sun's energy output varies not just with the 11-year cycle, but also with much longer-term changes that may influence Earth's climate over centuries and millennia. Proxy records from tree rings, ice cores, and marine sediments suggest that the sun has experienced extended periods of unusually low activity, such as the Maunder minimum of the 17th century, when very few sunspots were observed for several decades. During this time, Earth experienced cooler temperatures in many regions, leading to the period sometimes called the Little Ice Age. While solar variations alone cannot explain recent climate changes, these natural fluctuations in solar activity remind us that our star is not perfectly constant, but varies on multiple timescales in ways that can influence conditions on Earth. The sun creates its own version of weather patterns that are far more dramatic than anything experienced on Earth. Solar tornadoes, made of superheated plasma following twisted magnetic field lines, can tower hundreds of thousands of miles above the solar surface and persist for hours or days. Solar tsunamis, waves of hot gas triggered by solar flares, can race across the sun's surface at speeds of hundreds of miles per second, lifting material high into the corona before it crashes back down. These phenomena operate on scales that dwarf terrestrial weather systems, with individual solar storms capable of affecting regions larger than multiple Earth diameters. Yet despite their incredible size and power, these solar weather patterns follow physical principles similar to those governing earthly weather, driven by differences in temperature, pressure, and magnetic field strength, rather than the simpler meteorology we experience in Earth's atmosphere. The sun's gravitational field creates subtle but measurable effects on the precision timekeeping systems that modern civilization depends upon. The global positioning system satellites that enable navigation and synchronization around the world must account for both special and general relativistic effects caused by their motion through Earth's gravitational field and the sun's more distant but still significant gravitational influence. The sun's gravity also affects the orbits of artificial satellites around Earth, creating small perturbations that must be calculated and corrected in order to maintain accurate orbital predictions. Even the atomic clocks used to define official time standards are slightly affected by solar gravitational effects, though these influences are far too small to notice in everyday life. These relativistic corrections remind us that the sun's influence extends even to the fundamental measurement of time itself. Solar astronomers have discovered that the sun's magnetic field undergoes complete reversals during each 11-year cycle, with magnetic north and south poles trading places in a process that takes several years to complete. During these magnetic reversals, the sun's overall magnetic field becomes highly complex and disordered, before reorganizing itself with opposite polarity. These magnetic flip-flops affect the propagation of cosmic rays through the solar system, as charged particles from deep space must navigate through the sun's magnetic field to reach the inner planets. When the sun's magnetic field is well organized, it more effectively deflects cosmic rays. while during periods of magnetic chaos around solar maximum, more cosmic rays can penetrate to Earth's orbit. This creates an inverse relationship between solar activity and cosmic ray intensity, with implications for atmospheric chemistry and possibly even cloud formation processes. The sun's energy drives not only the obvious processes we see around us, but also powers the subtle electromagnetic phenomena that surround our planet. The ionosphere, a layer of electrically charged particles created by solar ultraviolet radiation, forms a conductive shell around Earth that participates in a global electrical circuit. This circuit carries currents between the ionosphere and Earth's surface, with thunderstorms acting as generators that maintain the electrical potential difference between ground and sky. Solar activity can dramatically alter the properties of this ionospheric conductor, sometimes enhancing the global circuit and other times disrupting it entirely. The result is that solar storms can affect not only technological systems, but also the natural electrical environment of our planet, influencing everything from lightning patterns to the behavior of animals that navigate using electromagnetic cues. The sun's interior contains layers with distinctly different properties and behaviors, like a cosmic onion with each shell operating according to its own physical rules. The innermost core, where nuclear fusion occurs, has temperatures exceeding 15 million degrees and pressures more than 200 billion times greater than Earth's atmosphere. Surrounding this is the radiative zone, where energy slowly diffuses outward through countless interactions with matter, taking thousands of years to traverse this region. Above that lies the convection zone, where hot plasma rises and cool plasma sinks in giant circulation cells that transport energy to the surface much more quickly. Each of these layers rotates at slightly different rates and has its own magnetic properties, contributing to the sun's overall complexity and the rich variety of phenomena we observe on its surface and in its atmosphere. The sun's relationship with the interstellar medium through which our solar system travels creates a dynamic boundary that changes over thousands of years. As our star moves through the galaxy, it encounters regions of varying density, temperature, and magnetic field strength, causing the heliosphere to expand and contract like a cosmic breathing process. Currently, our solar system appears to be entering a region of slightly denser interstellar material, which may gradually compress the heliosphere and allow more cosmic rays to penetrate the inner solar system. These changes occur so slowly that they're imperceptible during human lifetimes, but over geological timescales, they may influence Earth's climate through their effects on cosmic ray intensity and atmospheric chemistry. The sun's journey through the galaxy thus creates a very long-term cycle of environmental change that operates on timescales comparable to the evolution of complex life on Earth. Solar energy powers the hydrological cycle that distributes fresh water around our planet, creating the rain and snow that fill rivers and lakes and sustain terrestrial ecosystems. The sun's heat evaporates water from oceans, lakes, and rivers, lifting trillions of gallons of water vapor into the atmosphere where it can travel thousands of miles before condensing and falling as precipitation. This solar-powered water cycle operates continuously, recycling the same water molecules through evaporation, condensation, and precipitation in an endless loop that has continued for billions of years. Without the sun's energy to drive evaporation, Earth's water would remain locked in the oceans, leaving the continents as barren deserts. The gentle warmth of sunlight thus creates not only the energy that powers life, but also the fresh water that makes terrestrial life possible. The sun's magnetic field creates a complex three-dimensional structure throughout the solar system that influences the behavior of charged particles from sources both near and far. Cosmic rays from distant supernovas and other galactic sources must navigate through this magnetic labyrinth to reach Earth, with their paths deflected and scattered by magnetic irregularities in the solar wind. The result is that cosmic ray intensity at Earth varies not only with solar activity, but also with the detailed structure of interplanetary magnetic fields. During some periods, cosmic rays can reach Earth more easily along certain magnetic field lines, while during other times they are more effectively excluded by magnetic barriers. This creates complex patterns of cosmic ray variation that space physicists are still working to fully understand and predict. The sun's energy reaches Earth in the form of photons that have traveled across 93 million miles of empty space, carrying with them information about conditions in the solar atmosphere at the time they were emitted. Each wavelength of light tells a different story about solar processes, from the deep red light of hydrogen emissions to the brilliant blue-white glow of the solar continuum. Spectroscopic analysis of sunlight reveals the presence of dozens of different chemical elements in the solar atmosphere, each leaving its own characteristic fingerprint in the spectrum of solar radiation. These spectral lines not only tell us what the sun is made of, but also reveal information about temperature, pressure, magnetic field strength, and motion in different layers of the solar atmosphere. In this way, sunlight serves as a cosmic messenger, delivering detailed information about our star's physical properties across the vast gulf of space. The sun creates its own version of seasons through the 11-year cycle of magnetic activity, with each cycle bringing changes in solar behavior that affect the entire solar system. During solar minimum, the sun appears quiet and stable, with few sunspots and minimal magnetic activity. As the cycle progresses towards solar maximum, magnetic complexity increases, sunspots multiply, and the frequency of flares and coronal mass ejections rises dramatically. This solar seasonal cycle affects everything from satellite operations to radio communications to the intensity of auroral displays. Space weather forecasters monitor solar activity as carefully as meteorologists track atmospheric weather, knowing that a major solar storm can disrupt technological systems and create beautiful auroral displays simultaneously. The sun's immense gravitational field creates tidal effects throughout the solar system, gently stretching and compressing celestial bodies in ways that can influence their internal structure and geological activity. Even Earth experiences solar tides in its solid rock, with the planet's surface rising and falling by several inches twice each day in response to the sun's gravitational pull. These earth tides are much smaller than ocean tides, but are still measurable with sensitive instruments. On other planets and moons throughout the solar system, tidal heating from both the sun and nearby massive planets can generate internal heat that drives geological processes and may even maintain subsurface oceans beneath icy crusts. The sun's gravity thus reaches across millions of miles to influence the internal dynamics of worlds throughout the solar system. The sun's energy drives atmospheric circulation patterns that distribute heat, moisture, and momentum around our planet in complex three-dimensional flows. The Hadley circulation, named after the 18th century physicist who first described it, carries hot air from the tropics toward the poles in the upper atmosphere while returning cooler air toward the equator at ground level. This solar-powered circulation creates the trade winds that early sailors depended upon for ocean voyages and continues to influence weather patterns today. Similar circulation cells exist at higher latitudes, creating the prevailing westerly winds of temperate regions and the polar easterlies of high latitudes. These atmospheric rivers of air, powered ultimately by solar energy, transport not only heat but also water vapor, dust, pollen, and other materials around the globe, connecting distant regions through invisible aerial highways. The sun produces neutrinos at such a prodigious rate that about 65 billion of these ghostly particles pass through each square centimeter of Earth's surface every second. These nearly massless particles are created as a byproduct of nuclear fusion in the solar core and escape immediately into space, carrying with them direct information about the nuclear reactions happening in the sun's heart at this very moment. Unlike photons, which can take thousands of years to journey from the core to the surface, neutrinos interact so weakly with matter that they stream directly through the sun as if it were transparent. Special underground detectors filled with thousands of tons of water or other materials can occasionally catch one of these elusive particles, providing astronomers with a real-time window into solar nuclear processes that would otherwise be completely hidden from view. The sun's magnetic field lines sometimes form closed loops that trap hot plasma high above the solar surface, creating the graceful arcing structures known as prominences. These magnetic cages can hold material at temperatures of tens of thousands of degrees, suspended against the pull of solar gravity for days, weeks, or even months. When viewed against the darkness of space during a solar eclipse, prominences appear as delicate pink or red features that seem to dance and flow along invisible magnetic highways. Some prominences remain relatively stable, slowly evolving as they follow the sun's rotation, while others can suddenly erupt, launching their trapped material into space at speeds exceeding escape velocity. The largest prominences can extend for distances greater than the diameter of several Earths, creating majestic displays of the power of magnetic forces to shape and control matter in the solar atmosphere. The sun's influence on Earth extends beyond the atmosphere to affect even the solid ground beneath our feet through the complex interactions between solar activity and Earth's magnetic field. During geomagnetic storms triggered by solar events, electric currents induced in Earth's magnetosphere can create corresponding currents in the conducting layers of our planet's interior. These telluric currents flowing through rock and underground water can affect everything from pipeline corrosion to the accuracy of magnetic navigation systems. Geologists and geophysicists monitor these Earth currents as part of space weather research, recognizing that solar storms create electrical disturbances that propagate not only through the atmosphere but also through the solid Earth itself. The sun's corona, visible during total solar eclipses as a shimmering halo of pearl white light, extends millions of miles into space with streamers and rays that reveal the complex structure of solar magnetic fields. These coronal streamers follow magnetic field lines that arch high above the solar surface before curving back to connect with regions of opposite magnetic polarity. The corona's temperature of over 1,000,000 degrees creates conditions unlike anything found naturally on Earth, where matter exists in a state of plasma so hot that electrons are stripped from their atoms. This superheated gas flows outward from the sun at speeds that eventually exceed escape velocity, becoming the solar wind that fills the entire solar system. The corona's ethereal beauty during eclipses has inspired observers for thousands of years, yet its extreme physical conditions represent one of the most hostile environments in the solar system. Solar scientists study the sun's activity using a technique called Doppler imaging, which can detect motions in the solar atmosphere with incredible precision. By measuring tiny shifts in the wavelength of light from different regions of the sun, astronomers can create maps showing where material is moving toward or away from Earth at speeds of just a few miles per hour. These velocity measurements reveal the detailed structure of solar convection, the rotation of different layers within the sun, and the motions of plasma in the solar atmosphere. Doppler imaging has shown that the sun's surface is covered with granules of rising and falling gas, each about the size of a terrestrial continent, that constantly churn and change as hot plasma rises from below and cooler plasma sinks back into the solar interior. The sun's energy output varies slightly with its 11-year magnetic cycle, but these variations are so small that they require extremely precise satellite measurements to detect. The total solar irradiance, or solar constant, changes by only about 1/10% between solar minimum and solar maximum. Yet even this tiny variation has measurable effects on Earth's upper atmosphere. During periods of high solar activity, increased ultraviolet radiation heats and expands the thermosphere, increasing atmospheric drag on low-orbiting satellites and requiring more frequent orbital corrections. Solar irradiance measurements from space have revealed that our star is remarkably stable compared to many other stars, varying far less than would be expected based on its magnetic activity level. This stability has been crucial for the development and maintenance of life on Earth. The sun creates a vast magnetic bubble around the solar system that protects us from most of the high-energy radiation that permeates interstellar space. This heliosphere, shaped by the interaction between solar wind and the interstellar medium, extends far beyond the orbit of Pluto to distances of over 100 astronomical units from the sun. The heliopause, where solar wind pressure finally balances interstellar pressure, marks the boundary between the solar system and interstellar space. When the Voyager spacecraft crossed this boundary, they detected dramatic changes in the cosmic ray environment, confirming that the sun's magnetic influence creates a partially shielded cavity in which the planets orbit. Without this heliospheric protection, Earth and the other planets would be exposed to much higher levels of galactic cosmic radiation. The sun's gravitational influence extends far into the outer reaches of the solar system, where it holds sway over the Oort cloud, a vast spherical shell of comets that may contain trillions of icy objects. These distant members of the solar system orbit at distances up to halfway to the nearest star, taking millions of years to complete single orbits around the sun. Occasionally, gravitational perturbations from passing stars or galactic tides nudge one of these distant comets toward the inner solar system, beginning a journey that may take hundreds of thousands of years, but will eventually bring the comet close enough to the sun to develop the glowing tail that makes it visible from Earth. In this way, the sun continues to interact with the most remote members of its family, occasionally calling them home from the frozen depths of space for brief, spectacular visits to the warm inner regions, where life flourishes on a small blue planet. The sun's magnetic field creates invisible sculptures in space that dwarf any artwork ever created by human hands. These magnetic structures, carved from pure energy and plasma, can tower millions of miles above the solar surface in graceful arcs that follow field lines like cosmic architecture. Solar prominences trace these invisible paths, creating bridges of glowing gas that span distances greater than the space between Earth and Moon. When these magnetic sculptures suddenly collapse or reconfigure, they release energy equivalent to billions of nuclear explosions. Yet from our distant vantage point, they appear as gentle brightenings against the solar disk. The sun is constantly reshaping these magnetic masterpieces, building and destroying structures of such immense scale that entire planets could pass through them without touching their glowing walls. Solar storms create ripple effects that travel outward through space like invisible tsunamis, carrying the sun's influence to the farthest reaches of the solar system. When a coronal mass ejection erupts from the solar surface, it creates a shock wave in the solar wind that can accelerate particles to incredible energies and compress planetary magnetospheres throughout the solar system. These interplanetary disturbances can take days to reach Earth, but their effects may persist for weeks as our planet's magnetic field slowly recovers from the impact. The largest solar storms can affect multiple planets simultaneously, creating a solar system-wide response to a single magnetic eruption on our star's surface. Even now, as you rest in the darkness, shock waves from solar storms that erupted days ago may be washing over Earth's magnetic field, creating subtle auroral glows at the poles and gentle fluctuations in the planet's electromagnetic environment. The sun breathes with rhythms that span not just minutes or hours, but decades and centuries, in cycles within cycles that create a complex temporal symphony. Beyond the familiar 11-year sunspot cycle lies a 22-year magnetic cycle, as the sun's magnetic field takes 2 complete sunspot cycles to return to its original polarity. Longer rhythms of 88 years and even multi-century patterns have been detected in historical records, suggesting that our star operates according to clockwork mechanisms we're only beginning to understand. These extended cycles may influence Earth's climate in subtle ways, creating variations in temperature and weather patterns that occur so slowly they're difficult to distinguish from random fluctuations. The sun's temporal rhythms remind us that even seemingly chaotic systems often contain hidden orders, patterns within patterns that reveal themselves only to patient observation across generations. Sunlight carries within it a complete electromagnetic symphony, with each wavelength playing its own unique role in the cosmic composition that sustains life on Earth. Radio waves from the sun whisper information about magnetic fields and particle acceleration in the corona, while infrared radiation provides the gentle warmth that maintains Earth's temperature. Visible light powers photosynthesis and creates the blue sky through atmospheric scattering. Ultraviolet radiation generates the ozone layer that protects life from harmful radiation, and tiny amounts of X-rays and gamma rays reveal the most energetic processes occurring in the solar atmosphere. This complete spectrum of electromagnetic energy arrives at Earth as a perfectly orchestrated blend, each component essential for maintaining the delicate balance that allows our planet to remain habitable. When you feel sunshine warming your skin, you're experiencing not just visible light, but the culmination of this entire electromagnetic symphony playing across your body. The sun's interior operates as a vast nuclear engine with multiple chambers, each contributing to the overall process that converts hydrogen into the light and heat that sustain our solar system. In the innermost core, temperatures and pressures create conditions so extreme that hydrogen nuclei overcome their electrical repulsion and fuse into helium, releasing tremendous amounts of energy in the process. This energy then begins its epic journey outward, first through the radiative zone, where it bounces from atom to atom in a cosmic pinball game lasting tens of thousands of years. Finally reaching the convection zone, the energy is carried upward by massive circulation cells of hot plasma that transport it to the surface much more quickly. Each layer of this solar engine operates according to its own physical principles, yet all work together to maintain the steady energy output that has remained remarkably constant throughout Earth's history. Solar wind sculpts the magnetospheres of planets throughout the solar system, creating unique interactions that depend on each world's magnetic properties and atmospheric characteristics. Earth's strong magnetic field deflects most solar wind particles around the planet, creating a protective cavity called the magnetosphere that shields our atmosphere from erosion. Mars, lacking a global magnetic field, has gradually lost much of its atmosphere to solar wind erosion over billions of years. Jupiter's enormous magnetosphere captures solar wind particles and accelerates them to such high energies that the planet glows in radio wavelengths, while Venus's thick atmosphere interacts directly with the solar wind to create a complex wake structure on the planet's night side. These diverse planetary responses to the same solar wind demonstrate how local conditions can dramatically alter the effects of our star's influence across the solar system. The sun's energy drives plate tectonics on Earth through a complex chain of processes that connect stellar nuclear fusion to the movement of continents. Solar heating creates temperature differences that drive atmospheric circulation, which in turn influences ocean currents and the distribution of water around the globe. This water eventually finds its way into Earth's interior through subduction zones, where it acts as a lubricant that facilitates the movement of tectonic plates. The sun's energy also powers the erosion and weathering processes that create sediments, which are then recycled through the mantle via plate tectonics. Without solar energy to drive this complex system, Earth's surface would likely remain geologically static, locked in place without the dynamic processes that create mountains, ocean basins, and the varied landscapes that characterize our planet. Coronal holes appear as dark regions in X-ray images of the sun, but they represent gateways through which high-speed solar wind streams escape into space with unusual ease. These regions, where the sun's magnetic field lines extend outward rather than looping back to the surface, allow solar wind particles to accelerate to speeds twice as fast as the normal solar wind. When these high-speed streams encounter Earth's magnetosphere several days later, they can trigger beautiful auroral displays and minor geomagnetic disturbances that persist for days as our planet rotates through the stream. Coronal holes can persist for months, creating recurring patterns of geomagnetic activity as they rotate with the sun and repeatedly direct fast solar wind toward Earth. These seemingly empty regions of the corona thus serve as windows through which the sun's interior energy can more directly influence the space environment throughout the solar system. The sun creates its own weather patterns that operate on scales and timescales far beyond anything experienced on Earth, yet follow surprisingly similar physical principles. Solar granules, convection cells about the size of Texas, rise and fall across the sun's surface in patterns that resemble boiling water when viewed through powerful telescopes. These granules form as hot plasma rises from the solar interior, spreads out at the surface, cools, and then sinks back down in a continuous circulation that transports energy from deep within the sun to its visible surface. Supergranules, much larger convection cells spanning tens of thousands of miles, operate on longer timescales and help organize the sun's magnetic field into the complex patterns we observe. These solar weather systems demonstrate that convection, one of the most fundamental heat transport mechanisms in nature, operates across an enormous range of scales from laboratory experiments to stellar interiors. Solar flares represent some of the most powerful explosions in the solar system, yet they begin with the simple reconnection of magnetic field lines that have become twisted and stressed beyond their breaking point. When these invisible magnetic structures suddenly snap and reconfigure, they can release energy equivalent to billions of nuclear weapons in just a few minutes, accelerating particles to nearly the speed of light and heating plasma to temperatures exceeding 100 million degrees. The resulting burst of electromagnetic radiation races outward at the speed of light, reaching Earth in just 8 minutes and potentially disrupting radio communications and satellite operations. Meanwhile, the energetic particles accelerated by the flare follow a more leisurely journey along magnetic field lines, arriving at Earth hours or days later to create enhanced auroral displays and elevated radiation levels in space. These magnificent displays of magnetic energy remind us that the sun, despite its apparent steadiness, harbors forces of almost unimaginable power. The sun's influence on Earth's climate operates through mechanisms both direct and indirect, from the obvious warming that drives weather patterns to subtle effects on atmospheric chemistry that can influence climate over decades or centuries. Variations in solar ultraviolet output, though small in absolute terms, can significantly affect the formation and destruction of ozone in Earth's stratosphere, altering the temperature structure of the upper atmosphere in ways that cascade down to influence surface weather patterns. Solar energetic particles can enhance the production of nitrogen oxides in the atmosphere, which then participate in complex chemical reactions that affect both ozone concentrations and the greenhouse properties of the atmosphere. These solar climate connections operate on such long timescales that their effects are difficult to separate from other climate influences. Yet they may help explain some of the subtle climate variations observed in historical records. The sun's magnetic field extends throughout the solar system in a complex, three-dimensional structure that influences the propagation of cosmic rays from distant galaxies. High-energy particles accelerated by supernovas and other violent galactic events must navigate through this magnetic labyrinth to reach the inner solar system, with their paths scattered and deflected by magnetic irregularities in the solar wind. During periods of high solar activity, when the interplanetary magnetic field is more turbulent and disorganized, cosmic rays are more effectively excluded from the inner solar system. Conversely, during solar minimum periods when the magnetic field is more regular and organized, cosmic rays can more easily penetrate to Earth's orbit. This creates an inverse relationship between solar activity and cosmic ray intensity that affects atmospheric chemistry and may influence cloud formation processes through mechanisms that scientists are still working to understand. Solar energy powers the global water cycle that distributes fresh water around our planet, creating the precipitation patterns that sustain terrestrial ecosystems and human civilization. The sun's heat evaporates approximately 125 trillion gallons of water from Earth's oceans every day, lifting this moisture into the atmosphere where it can travel thousands of miles before condensing and falling as rain or snow. This solar-powered atmospheric river system transports not only water but also energy, as the latent heat released during condensation helps drive atmospheric circulation patterns. Regional variations in solar heating create the monsoon systems that bring seasonal rains to billions of people, while the annual cycle of solar energy input drives the seasonal patterns of precipitation that ecosystems and agricultural systems depend upon. Without the sun's energy to power evaporation, Earth's continents would remain barren deserts, unable to support the rich terrestrial biosphere we see today. The sun's gravitational field creates subtle but measurable effects on the passage of time itself, demonstrating Einstein's prediction that massive objects can warp the fabric of space and time. Atomic clocks placed at different distances from the sun would tick at slightly different rates, with those closer to our star running more slowly due to gravitational time dilation. This effect is far too small to notice in everyday life, but it's large enough that the global positioning system satellites orbiting Earth must account for both the sun's and Earth's gravitational effects on time in order to maintain their navigation accuracy. The sun's gravity also bends light rays passing near it, creating a gravitational lens that can slightly magnify and distort images of background stars. These relativistic effects remind us that the sun's influence extends beyond simple gravitational attraction to affect the very structure of space and time throughout the solar system. Solar astronomers have discovered that the sun rings like an enormous bell, vibrating in millions of different oscillation modes that reveal details about its internal structure. These stellar seismic waves, created by turbulent convection in the sun's outer layers, bounce back and forth through the solar interior, like sound waves echoing in a cathedral. By analyzing the periods and patterns of these oscillations, scientists can map the sun's internal density, temperature, and rotation profiles with remarkable precision. Some of these solar vibrations have periods of just 5 minutes, while others take hours to complete one cycle. The sun's surface rises and falls by tiny amounts as these waves propagate, creating a complex pattern of motion that requires sensitive instruments to detect, but provides invaluable information about processes occurring deep within our star's hidden interior. The sun's corona extends its influence far beyond what we can see during eclipses, creating a dynamic environment that fills the entire inner solar system with its presence. This superheated outer atmosphere, with temperatures exceeding 1 million degrees, generates the solar wind that streams continuously outward at speeds of hundreds of miles per second. The corona's magnetic field lines, carried along by this flow of charged particles, create invisible highways through space that guide the movement of energetic particles and influence the magnetic environments of planets throughout the solar system. During periods of high solar activity, the corona can erupt in spectacular displays, visible to specialized telescopes on Earth, launching billions of tons of magnetized plasma into interplanetary space in events that demonstrate the incredible power contained within this seemingly delicate stellar atmosphere. Solar radiation pressure, though incredibly gentle, has measurable effects throughout the solar system that accumulate over time to influence the orbits of small objects. Photons of sunlight carry tiny amounts of momentum, and when they strike dust particles or spacecraft, they exert forces that can gradually alter trajectories over months or years. This radiation pressure is what shapes comet tails, pushing dust and gas away from the comet's nucleus to create the magnificent streaming displays that have inspired wonder throughout human history. Spacecraft designers must account for solar radiation pressure when planning long-duration missions, as the cumulative effect can significantly change a spacecraft's orbit over time. Engineers have even learned to harness this gentle cosmic wind with solar sails, using large reflective surfaces to catch sunlight and propel spacecraft without carrying any fuel, demonstrating that light itself can serve as a means of transportation through the solar system. The sun's energy reaches Earth in precisely measured quantities that form the foundation for understanding our planet's energy balance and climate system. The solar constant, approximately 1,361 watts per square meter, represents the amount of solar energy received at the top of Earth's atmosphere. This energy input drives virtually all weather and climate processes, from the formation of clouds and precipitation to the circulation patterns that distribute heat around the globe. Climate scientists use precise measurements of solar irradiance from satellites to monitor how our star's energy output varies over time, providing crucial data for understanding both natural climate variations and human influences on Earth's energy balance. Even tiny changes in solar output measured to fractions of a percent can have detectable effects on Earth's climate system over time. The sun's magnetic field undergoes dramatic reversals during each solar cycle, with magnetic north and south poles trading places in a process that affects the entire solar system. These magnetic flip-flops occur gradually over several years, during which time the sun's overall magnetic field becomes highly complex and disorganized before reorganizing itself with opposite polarity. The magnetic reversal process influences how cosmic rays from distant galaxies propagate through the solar system, as these high-energy particles must navigate through the changing magnetic landscape of interplanetary space. During periods when the sun's magnetic field is in transition, cosmic ray intensity at Earth can fluctuate significantly, creating variations in atmospheric ionization that may affect everything from cloud formation to atmospheric chemistry. These magnetic reversals demonstrate that even the sun's most fundamental properties are not permanent, but evolve in regular cycles that connect our star to the broader galactic environment. Solar energy drives the formation and behavior of Earth's atmospheric layers, creating the complex vertical structure that protects life at the surface while enabling weather and climate processes. Solar ultraviolet radiation creates the ionosphere, a layer of charged particles that reflects radio waves and participates in the global electrical circuit connecting ground to sky. Solar heating of the stratosphere, enhanced by the absorption of ultraviolet radiation by ozone, creates the temperature inversion that defines this atmospheric layer and influences the circulation patterns that affect surface weather. Even the highest atmospheric layers, hundreds of miles above Earth's surface, expand and contract in response to solar activity, affecting the drag experienced by low-orbiting satellites, and requiring frequent adjustments to their orbits. The sun's energy thus shapes Earth's atmosphere from the ground to the edge of space, creating the protective envelope that makes life possible on our planet's surface. The sun's influence extends to the very atoms that make up our bodies, as the nuclear processes occurring in stellar cores throughout the galaxy have created virtually every chemical element heavier than hydrogen and helium. The carbon atoms in our DNA, the oxygen we breathe, the calcium in our bones, and the iron in our blood were all forged in the nuclear furnaces of massive stars that lived and died before our sun was born. When these ancient stars exhausted their fuel and exploded as supernovas, they scattered these heavy elements throughout space, where they were eventually incorporated into the gas cloud that collapsed to form our solar system. The sun continues this cosmic alchemy on a smaller scale, steadily converting hydrogen into helium through nuclear fusion and creating the energy that sustains all life on Earth. In a very literal sense, we are children of the stars, made from materials created in stellar furnaces and powered by the ongoing nuclear reactions in our own star. The sun creates temporal rhythms that extend far beyond the daily cycle of day and night, establishing longer periodicities that influence everything from seasonal weather patterns to multi-decade climate variations. The annual cycle of solar heating caused by Earth's tilted axis and elliptical orbit drives the progression of seasons that ecosystems and human societies have adapted to over millennia. Longer-term variations in Earth's orbital parameters, known as Milankovitch cycles, alter the distribution of solar energy across latitudes and seasons over thousands of years, triggering ice ages and warm periods that have shaped the evolution of life on our planet. Even the sun's own internal cycles, particularly the 11-year sunspot cycle and longer magnetic variations, create subtle but measurable influences on Earth's climate that operate on timescales spanning decades to centuries. These overlapping solar rhythms create a complex temporal symphony that has been playing since the formation of the solar system. Solar-wind interactions with planetary magnetic fields create some of the most beautiful and dynamic phenomena in the solar system, from the shimmering auroras that dance across polar skies to the invisible magnetic reconnection events that can explosively release stored energy. When the solar wind encounters Earth's magnetosphere, it can trigger a cascade of processes that channel energetic particles into our planet's upper atmosphere, where they collide with oxygen and nitrogen molecules to create the colorful lights we see as auroras. These same processes occur throughout the solar system wherever solar wind encounters planetary magnetic fields, creating auroral displays on Jupiter, Saturn, and other magnetized planets that can be far more intense than anything seen on Earth. The interaction between solar wind and planetary magnetospheres represents one of the fundamental ways that our star continues to shape and influence the environments of worlds throughout the solar system, connecting them all through invisible threads of magnetic force and flowing plasma. The sun's energy creates invisible rivers in our atmosphere that carry heat, moisture, and life itself across vast distances in patterns so elegant they seem choreographed by cosmic forces. These atmospheric currents, powered by the simple act of solar heating, create the trade winds that early explorers relied upon to cross oceans, the monsoons that bring life-giving rains to billions of people, and the jet streams that guide weather systems around our planet like high-altitude highways carved from moving air. When solar energy warms the equatorial regions more intensely than the poles, it sets in motion a planetary circulation system that operates continuously, day and night, season after season, distributing the sun's gift of warmth to every corner of our world. These atmospheric rivers carry not just air, but the very essence of climate itself, transporting tropical warmth toward the poles and returning cooler air toward the equator in an endless dance that has continued for billions of years. The sun's magnetic field creates structures in space so vast and intricate that they dwarf the grandest cathedrals ever built by human hands. These invisible magnetic architectures, spanning millions of miles and shaped by forces beyond our everyday experience, guide the flow of charged particles through the solar system like cosmic highways made of pure energy. Solar wind follows these magnetic pathways as it streams outward from our star, carrying the sun's magnetic personality to every planet, moon, and asteroid in its gravitational embrace. When these magnetic field lines become twisted and strained beyond their breaking point, they can suddenly snap and reconnect with explosive violence, releasing more energy in a few minutes than human civilization has used throughout its entire history. Yet from our distant perspective, these magnetic cataclysms appear as gentle brightenings against the solar disk, reminding us that even the most powerful forces in nature can seem peaceful when viewed from afar. Solar storms create ripple effects that propagate through space like invisible waves on a cosmic ocean, carrying disturbances that can affect every world in our solar system simultaneously. When a coronal mass ejection erupts from the sun's surface, it launches billions of tons of magnetized plasma into space at speeds that can exceed 1,000,000 miles per hour, creating shock waves in the solar wind that compress and distort planetary magnetic fields throughout the solar system. These interplanetary disturbances can take days to cross the gulf between Sun and Earth, but their arrival can trigger cascading effects that persist for weeks as our planet's magnetic field slowly recovers from the impact. The largest solar storms can affect multiple planets at once, creating a solar system-wide response to a single magnetic eruption on our star's surface, demonstrating how intimately connected all the worlds in our cosmic neighborhood truly are. The sun breathes with rhythms that span not just hours or days, but decades and centuries in cycles within cycles that reveal the deep, temporal architecture underlying stellar behavior. Beyond the familiar 11-year sunspot cycle lies a 22-year magnetic cycle, as our star's magnetic field requires 2 complete sunspot cycles to return to its original polarity and orientation. Even longer rhythms spanning 88 years, 200 years, and perhaps millennia have been detected in historical records and proxy data, suggesting that the sun operates according to clockwork mechanisms of staggering complexity and precision. These extended cycles may influence Earth's climate in subtle ways, creating variations in temperature and weather patterns that unfold so slowly they can be difficult to distinguish from random fluctuations. The sun's temporal symphony reminds us that beneath the apparent chaos of solar activity lies a hidden order, patterns within patterns that reveal themselves only through patient observation across generations of human lifetimes. Sunlight carries within its gentle embrace a complete electromagnetic orchestra, with each wavelength playing its own essential role in the cosmic composition that sustains life throughout our solar system. Radio waves whisper information about magnetic fields dancing in the corona, while infrared radiation provides the steady warmth that maintains Earth's perfect temperature for liquid water. Visible light powers the photosynthetic processes that form the foundation of virtually every food chain on our planet. Ultraviolet radiation creates and maintains the protective ozone layer that shields us from harmful cosmic rays, and tiny amounts of higher energy radiation reveal the most energetic processes occurring deep within the solar atmosphere. This complete spectrum arrives at Earth as a perfectly balanced blend, each component precisely calibrated to support the delicate chemical and physical processes that make life possible. When you step into sunlight and feel its warmth on your skin, you are experiencing not just visible light, but the culmination of this entire electromagnetic symphony playing gently across your body. The sun's interior operates as a vast nuclear furnace with multiple chambers, each contributing its own essential role to the overall process that transforms simple hydrogen into the light and heat that illuminate our days and warm our nights. In the innermost core, where temperatures exceed 15 million degrees and pressures reach values almost beyond imagination, hydrogen nuclei overcome their natural electrical repulsion to fuse together, releasing tremendous quantities of energy that begin an epic journey toward the surface. This energy must first traverse the radiative zone, a region so dense that individual photons can spend tens of thousands of years bouncing from atom to atom to atom in a cosmic game of pinball, before finally escaping to the convection zone above. There, massive circula, T cells of superheated plasma carry the energy upward much more quickly, completing the final stage of its journey to the sun's visible surface, where it can finally escape into space as the sunlight that sustains our world. Solar wind sculpts the magnetic environments of planets throughout our solar system, creating unique interactions that depend on each world's individual magnetic properties and atmospheric characteristics. Earth's robust magnetic field deflects most solar wind particles around our planet, creating a protective magnetic cavity that shields our atmosphere from the erosive effects of this stellar breeze. Mars, lacking a global magnetic field, has gradually lost much of its original atmosphere to solar wind erosion over billions of years, transforming from a potentially habitable world into the cold, dry desert we observe today. Jupiter's enormous magnetosphere traps solar wind particles and accelerates them to such incredible energies that the giant planet actually glows in radio wavelengths, while Venus's thick atmosphere interacts directly with the solar wind to create complex wake structures on the planet's night side. These diverse planetary responses to the same solar wind demonstrate how local conditions can dramatically alter the effects of our star's influence across the vast reaches of space. The sun's energy drives the dynamic process of plate tectonics on Earth through an intricate chain of connections that link stellar nuclear fusion to the gradual movement of continents across our planet's surface. Solar heating creates the atmospheric temperature differences that drive global wind patterns, which in turn influence ocean currents and the distribution of water vapor around our world. This water eventually finds its way deep into Earth's interior through subduction zones, where it acts as a crucial lubricant that facilitates the movement of massive tectonic plates. The sun's energy also powers the weathering and erosion processes that break down rocks and create the sediments that are eventually recycled through the mantle via plate tectonic processes. Without the sun's steady energy input to drive this complex system of interconnected processes, Earth's surface would likely remain geologically static, locked in place without the dynamic forces that create mountain ranges, ocean basins, and the constantly changing landscapes that characterize our living planet. Coronal holes appear as dark, empty regions in X-ray images of the sun, but they actually represent gateways through which high-speed streams of solar wind can escape into space with unusual freedom and velocity. These regions, where magnetic field lines extend outward into space rather than looping back to connect with the solar surface, allow solar wind particles to accelerate to speeds nearly twice as fast as the normal solar wind that flows from other regions of the corona. When these high-speed streams encounter Earth's magnetosphere several days after leaving the sun, they can trigger beautiful auroral displays and gentle geomagnetic disturbances that may persist for days as our planet rotates through the stream. Coronal holes can persist for months at a time, creating recurring patterns of space weather activity as they rotate with the sun and repeatedly direct fast solar wind streams toward Earth and other planets. These seemingly empty regions of the solar atmosphere thus serve as windows through which our star's interior energy can more directly influence the space environment throughout the entire solar system. The sun creates its own magnificent weather systems that operate on scales and timescales far beyond anything we experience on Earth. Yet they follow surprisingly similar physical principles to the atmospheric phenomena we observe in our own skies. Solar granules, convection cells roughly the size of terrestrial states, rise and fall across the sun's surface in patterns that closely resemble boiling water when viewed through powerful telescopes equipped with special filters. These granulation patterns form as columns of superheated plasma rise from deep within the solar interior, spread out horizontally when they reach the surface, cool through radiation into space, and then sink back down into the depths to complete the convection cycle. Larger structures called supergranules, spanning tens of thousands of miles and persisting for days at a time, help organize the sun's magnetic field into the complex patterns we observe and study. These solar weather systems demonstrate that convection, one of nature's most fundamental heat transport mechanisms, operates effectively across an enormous range of scales, from laboratory experiments to the interiors of stars. Solar flares represent some of the most powerful and spectacular explosions that occur anywhere in our solar system, yet they begin with the seemingly simple reconnection of magnetic field lines that have become twisted and stressed beyond their capacity to maintain structural integrity. When these invisible magnetic structures suddenly snap and reconfigure themselves, they can release amounts of energy equivalent to billions of nuclear weapons, detonating simultaneously, accelerating subatomic particles to nearly the speed of light and heating plasma to temperatures that exceed 100 million degrees. The resulting burst of electromagnetic radiation races outward from the sun at light speed, reaching Earth in just over 8 minutes and potentially disrupting radio communications, SAT, elite operations, and other technological systems that modern civilization depends upon. Meanwhile, the energetic particles accelerated by the flare follow more leisurely trajectories along curved magnetic field lines, arriving at Earth hours or days later to create enhanced auroral displays and elevated radiation levels throughout the space environment surrounding our planet. The sun's influence on Earth's climate operates through mechanisms both obvious and remarkably subtle, ranging from the direct warming that drives daily weather patterns to complex effects on atmospheric chemistry that can influence climate conditions over periods spanning decades or centuries. Small variations in solar ultraviolet output, though representing only tiny fractions of the sun's total energy emission, can significantly affect the formation and destruction of ozone molecules in Earth's stratosphere, altering temperature profiles in the upper atmosphere in ways that cascade downward to influence surface weather patterns through complex feedback mechanisms. Solar energetic particles, accelerated to high speeds by flares and coronal mass ejections, production of nitrogen can enhance the oxides in the atmosphere, which then participate in intricate chemical reactions that affect both ozone concentrations and the greenhouse properties of various atmospheric gases. These solar climate connections operate on such extended timescales that their effects can be difficult to separate from other climate influences. Yet they may help explain some of the subtle climate variations that appear in historical records and paleoclimate data. The sun's magnetic field extends throughout the solar system in a complex three-dimensional structure that profoundly influences the propagation of cosmic rays streaming toward us from distant corners of our galaxy. High-energy particles accelerated by supernovas and other violent galactic phenomena must navigate through this magnetic labyrinth to reach the inner solar system, with their paths continuously scattered and deflected by magnetic irregularities embedded in the flowing solar wind. During periods of high solar magnetic activity, when the interplanetary magnetic field becomes more turbulent and disorganized, cosmic rays are more effectively excluded from the inner solar system through enhanced magnetic shielding. Conversely, during quiet periods when the magnetic field assumes more regular and predictable configurations, cosmic rays can more easily penetrate through the magnetic barriers to reach Earth's orbit and beyond. This creates an inverse relationship between solar activity levels and cosmic ray intensity that affects atmospheric chemistry and may influence cloud formation processes through mechanisms that atmospheric scientists are still working diligently to understand and quantify. Solar energy powers the magnificent global water cycle that distributes fresh water around our planet, creating the precipitation patterns that sustain terrestrial ecosystems, fill rivers and lakes, and provide the fresh water that human civilization absolutely requires for survival. The sun's radiant heat evaporates approximately 125 trillion gallons of water from Earth's oceans every single day, lifting this moisture high into the atmosphere where it can travel thousands of miles as invisible water vapor before condensing into droplets and falling back to the surface as rain, snow, or other forms of precipitation. This solar-powered atmospheric river system transports not only life-giving water, but also enormous amounts of latent heat energy, as the energy released due ring condensation helps drive the atmospheric circulation patterns that distribute weather systems around the globe. Regional variations in solar heating intensity create the monsoon systems that bring seasonal rains to billions of people, while the annual cycle of changing solar energy input drives the seasonal patterns of precipitation that natural ecosystems and agricultural systems have depended upon for millions of years. The sun's immense gravitational field creates subtle but scientifically measurable effects on the fundamental nature of time itself, providing real-world confirmation of Einstein's revolutionary prediction that massive objects can actually warp the fabric of space and time. Atomic clocks positioned at different distances from the sun would tick at slightly different rates, with those located closer to our star running measurably more slowly due to gravitational time dilation effects. While this phenomenon is far too small, it becomes significant to notice during ordinary human activities, enough that the global positioning system satellites orbiting Earth must account for both the Sun's and Earth's gravitational effects on the passage of time in order to maintain the precise timing accuracy that modern navigation systems require. The Sun's gravitational field also bends rays of light passing near it, creating a gravitational lensing effect that can slightly magnify and distort the apparent positions of background stars during solar eclipses. These relativistic effects serve as constant reminders that the Sun's influence extends far beyond simple gravitational attraction to affect the very structure of space and time throughout our entire solar system. Solar astronomers have made the remarkable discovery that our Sun rings like an enormous celestial bell, vibrating simultaneously in millions of different oscillation modes that reveal intimate details about the hidden structure of its interior regions. These stellar seismic waves, generated by the turbulent convection occurring in the Sun's outer layers, bounce back and forth through the solar interior like sound waves echoing endlessly through a vast cathedral of plasma and magnetic fields. By carefully analyzing the periods, amplitudes, and spatial patterns of these oscillations using sensitive instruments, scientists can map the Sun's internal density profiles, temperature gradients, and rotation rates with remarkable precision and detail. Some of these solar vibrations complete minutes, while others require full cycles in just several hours to finish a single oscillation. The Sun's visible surface rises and falls by microscopic amounts as these waves propagate through the stellar interior, creating an incredibly complex pattern of motion that requires the most sensitive scientific instruments to detect, but provides invaluable information about physical processes occurring deep within regions of our star that will forever remain hidden from direct observation. The Sun's corona extends its dynamic influence far beyond what becomes visible during the rare moments of total solar eclipses, creating an active and ever-changing environment that fills the entire inner solar system with its magnetic presence and energetic particles. This superheated outer atmosphere, maintaining temperatures that exceed 1 million degrees through processes that scientists are still working to fully understand, generates the continuous stream of solar wind that flows outward at speeds of hundreds of miles per second toward the outer boundaries of our solar system. The corona's complex magnetic field lines, carried along by this endless flow of charged particles, create invisible highways through interplanetary space that guide the movement of energetic particles and profoundly influence the magnetic environment surrounding planets throughout the solar system. During periods of heightened solar activity, the corona can erupt in spectacular displays visible to specialized telescopes and spacecraft, launching billions of tons of magnetized plasma into interplanetary space, in events that demonstrate the incredible power and energy contained within this seemingly delicate and ethereal stellar atmosphere. Solar radiation pressure, though almost impossibly gentle in its touch, accumulates measurable effects throughout the solar system over extended periods of time, gradually influencing the orbital trajectories of small objects and even large spacecraft during long-duration missions. Individual photons of sunlight carry infinitesimally small amounts of momentum, but when trillions upon trillions of these light particles strike dust grains, asteroids, or artificial satellites, they collectively exert forces that can slowly but persistently alter trajectories over months, years, or decades. This delicate radiation pressure is the primary force responsible for shaping the magnificent tails of comets, pushing microscopic dust particles and ionized gas away from the comet's nucleus, to create the streaming displays that have inspired wonder and awe throughout human history. Modern spacecraft engineers must carefully account for solar radiation pressure effects when planning long-duration interplanetary missions, as the cumulative influence can significantly modify a spacecraft's intended trajectory over time. Some visionary engineers have even learned to harness this gentle cosmic breeze by deploying solar sails, using large reflective surfaces to catch sunlight and propel spacecraft through the solar system without carrying any chemical fuel whatsoever. The sun's energy reaches our planet in precisely measured and carefully monitored quantities that form the fundamental foundation for understanding Earth's delicate energy balance and the complex climate system that makes our world habitable. The solar constant, representing approximately 1,361 watts of energy per square meter received at the top of Earth's atmosphere, provides the baseline energy input that drives virtually all weather phenomena, climate processes, ocean currents, and atmospheric circulation patterns that distribute heat around our globe. Climate scientists use incredibly precise measurements of solar irradiance obtained from sophisticated satellite instruments to continuously monitor how our star's energy output varies over time, providing crucial data necessary for understanding both natural climate variations and the human influences that are currently affecting Earth's energy balance in unprecedented ways. Even the tiniest changes in solar output, measured with precision to small fractions, ions of a single percent, can produce detectable effects on Earth's climate system when sustained over extended periods of time. And so our gentle journey through the sun's most peaceful secrets draws to a quiet close. We've traveled together from the nuclear furnace at our star's heart to the invisible boundaries where solar influence yields to the cosmic depths beyond. Along the way, we've discovered that our sun is far more than a simple source of light and warmth. It's a cosmic conductor orchestrating the symphony of our solar system, a stellar guardian whose magnetic embrace has sheltered life for billions of years, and a celestial timekeeper whose rhythms have marked the passage of ages since before consciousness first stirred on our small blue world. Tonight you've learned that every breath you take, every heartbeat, every thought drifting through your mind as you settle into sleep connects you to nuclear reactions occurring 93 million miles away. The carbon in your body was forged in ancient stellar furnaces. The oxygen you breathe was created when massive stars lived and died before our sun was born. And the gentle warmth you feel from sunlight began its journey in the solar core thousands of years ago. You are, quite literally, made of stardust powered by starlight, a living embodiment of cosmic processes that span both space and time. As you drift towards sleep, let these solar truths settle around you like a soft blanket of cosmic comfort. Tomorrow morning, when you wake, the same nuclear fires will still be burning in the sun's heart. The same solar wind will be whispering across space, and the same gentle magnetic field will be wrapping our solar system in its protective embrace. The sun will rise as it has for billions of years, carrying with it the promise of another day, powered by the most reliable energy source in our corner of the universe. Sleep well, knowing you're cradled in the warmth of starlight, and dream of the infinite cosmos that surrounds us all.